Remote sensing is the acquisition of information about an object or phenomenon without making physical contact with the object, and thus in contrast to in situ observation. In modern usage, the term generally refers to the use of aerial sensor technologies to detect and classify objects on Earth by means of propagated signals. It may be split into active remote sensing, when a signal is first emitted from aircraft or satellites, or passive when information is merely recorded. Overview. Passive sensors gather natural radiation that is emitted or reflected by the object or surrounding areas. Reflected sunlight is the most common source of radiation measured by passive sensors. Examples of passive remote sensors include film photography, infrared, charge-coupled devices, and radiometers. Active collection, on the other hand, emits energy in order to scan objects and areas, whereupon a sensor then detects and measures the radiation that is reflected or backscattered from the target. Radar and LiDAR are examples of active remote sensing where the time delay between emission and return is measured, establishing the location, speed and direction of an object. Remote sensing makes it possible to collect data on dangerous or inaccessible areas. Remote sensing applications include monitoring deforestation in areas such as the Amazon basin, glacial features in Arctic and Antarctic regions, and depth sounding of coastal and ocean depths. Military collection during the Cold War made use of standoff collection of data about dangerous border areas. Remote sensing also replaces costly and slow data collection on the ground, ensuring in the process that areas or objects are not disturbed. Orbital platforms collect and transmit data from different parts of the electromagnetic spectrum, which in conjunction with larger-scale aerial or ground-based sensing and analysis, provides researchers with enough information to monitor trends such as El Niño ±0 and other natural long- and short-term phenomena. Other uses include different areas of the earth sciences such as natural resource management, agricultural fields such as land usage and conservation, and national security and overhead, ground-based and standoff collection on border areas. Data acquisition techniques. The basis for multispectral collection and analysis is that of examined areas or objects that reflect or emit radiation that stand out from surrounding areas. For a summary of major remote sensing satellite systems, see the overview table. Applications of remote sensing data. Conventional radar is mostly associated with aerial traffic control, early warning, and certain large-scale meteorological data. Doppler radar is used by local law enforcement for unregistered trademark monitoring of speed limits and in enhanced meteorological collections such as wind speed and direction within weather systems, in addition to precipitation location and intensity. Other types of active collection includes plasmas and the ionosphere. Interferometric synthetic aperture radar is used to produce precise digital elevation models of large-scale terrain. Laser and radar altimeters on satellites have provided a wide range of data. By measuring the bulges of water caused by gravity, they map features on the seafloor to a resolution of a mile or so. By measuring the height and wavelength of ocean waves, the altimeters measure wind speeds and direction, and surface ocean currents and directions. Light detection and ranging is well known in examples of weapon ranging, laser-illuminated homing of projectiles. LiDAR is used to detect and measure the concentration of various chemicals in the atmosphere, while airborne LiDAR can be used to measure heights of objects and features on the ground more accurately than with radar technology. Vegetation remote sensing is a principal application of LiDAR. Radiometers and photometers are the most common instrument in use, collecting reflected and emitted radiation in a wide range of frequencies. The most common are visible and infrared sensors, followed by microwave, gamma ray and rarely, ultraviolet. They may also be used to detect the emission spectra of various chemicals, providing data on chemical concentrations in the atmosphere. Stereographic pairs of aerial photographs have often been used to make topographic maps by imagery and terrain analysts in trafficability and highway departments for potential routes. Simultaneous multispectral platforms such as Landsat have been in use since the 70s unregistered trademark S. These thematic mappers take images in multiple wavelengths of electromagnetic radiation and are usually found on Earth observation satellites, including the Landsat program or the ICONOS satellite. Maps of land cover and land use from thematic mapping can be used to prospect for minerals, detect or monitor land usage, deforestation, and examine the health of indigenous plants and crops, including entire farming regions or forests. Landsat images are used by regulatory agencies such as KYDOW to indicate water quality parameters including SECI depth, chlorophyll density and total phosphorus content. Weather satellites are used in meteorology and climatology. Hyperspectral imaging produces an image where each pixel has full spectral information with imaging narrow spectral bands over a contiguous spectral range. Hyperspectral images are used in various applications including mineralogy, biology, defense, and environmental measurements. Within the scope of the combat against desertification, remote sensing allows to follow up and monitor risk areas in the long term, to determine desertification factors, to support decision-makers in defining relevant measures of environmental management, and to assess their impacts. Geodetic, overhead geodetic collection was first used in aerial submarine detection and gravitational data used in military maps. This data revealed minute perturbations in the Earth, a unregistered trademark S gravitational field that may be used to determine changes in the mass distribution of the Earth, which in turn may be used for geological studies. Acoustic and near-acoustic, sonar, passive sonar, listening for the sound made by another object. Active sonar, emitting pulses of sounds and listening for echoes, used for detecting, ranging and measurements of underwater objects and terrain. Seismograms taken at different locations can locate and measure earthquakes by comparing the relative intensity and precise timings. To coordinate a series of large-scale observations, most sensing systems depend on the following: platform location, what time it is, and the rotation and orientation of the sensor. High-end instruments now often use positional information from satellite navigation systems. The rotation and orientation is often provided within a degree or two with electronic compasses. Compasses can measure not just azimuth, but also altitude, since the magnetic field curves into the Earth at different angles at different latitudes. More exact orientations require gyroscopic-aided orientation, periodically realigned by different methods including navigation from stars or known benchmarks. Data processing. Generally speaking, remote sensing works on the principle of the inverse problem. While the object or phenomenon of interest may not be directly measured, there exists some other variable that can be detected and measured, which may be related to the object of interest through the use of a data-derived computer model. The common analogy given to describe this is trying to determine the type of animal from its footprints. For example, while it is impossible to directly measure temperatures in the upper atmosphere, it is possible to measure the spectral emissions from a known chemical species in that region. The frequency of the emission may then be related to the temperature in that region via various thermodynamic relations. The quality of remote sensing data consists of his spatial, spectral, radiometric and temporal resolutions. Spatial resolution, the size of a pixel that is recorded in a raster image. Typically pixels may correspond to square areas ranging in site length from 1 to 1000 meters. Spectral resolution, the wavelength width of the different frequency bands recorded. Usually, this is related to the number of frequency bands recorded by the platform. Current Landsat collection is that of 7 bands, including several in the infrared spectrum, ranging from a spectral resolution of 0.07 to 2.1 I1/4 m. The Hyperion sensor on Earth observing 1 resolves 220 bands from 0.4 to 2.5 I1/4 m, with a spectral resolution of 0.10 to 0.11 I1/4 m per band. Radiometric resolution, the number of different intensities of radiation the sensor is able to distinguish. Typically, this ranges from 8 to 14 bits, corresponding to 256 levels of the grayscale and up to 16,384 intensities or shades of color, in each band. It also depends on the instrument noise. Temporal resolution, the frequency of flyovers by the satellite or plane, and is only relevant in time series studies or those requiring an averaged or mosaic image as in deforesting monitoring. This was first used by the intelligence community where repeated coverage revealed changes in infrastructure, the deployment of units or the modification introduction of equipment. Cloud cover over a given area or object makes it necessary to repeat the collection of said location. In order to create sensor-based maps, most remote sensing systems expect to extrapolate sensor data in relation to a reference point including distances between known points on the ground. This depends on the type of sensor used. For example, in conventional photographs, distances are accurate in the center of the image, with the distortion of measurements increasing the farther you get from the center. Another factor is that of the plate against which the film is pressed can cause severe errors when photographs are used to measure ground distances. The step in which this problem is resolved is called Geo Referencing, and involves computer-aided matching up of points in the image which is extrapolated with the use of an established benchmark, warping the image to produce accurate spatial data. As of the early 1990s, most satellite images are sold fully geo-referenced. In addition, images may need to be radiometrically and atmospherically corrected. Radiometric correction gives a scale to the pixel values, e.g. the monochromatic scale of 0 to 255 will be converted to actual radiance values. Topographic correction, in rugged mountains, as a result of terrain, the effective illumination of pixels varies considerably. In a remote sensing image, the pixel on this shady slope receives weak illumination and has a low radiance value. In contrast, the pixel on the sunny slope receives strong illumination and has a high radiance value. For the same object, the pixel radiance value on the shady slope will be different from that on the sunny slope. Additionally, different objects may have similar radiance values. These ambiguities seriously affected remote sensing image information extraction accuracy in mountainous areas. It became the main obstacle to further application of remote sensing images. The purpose of topographic correction is to eliminate this effect, recovering the true reflectivity or radiance of objects in horizontal conditions. It is the premise of quantitative remote sensing application. Atmospheric correction, elimination of atmospheric haze by rescaling each frequency band so that its minimum value corresponds to a pixel value of 0. The digitizing of data also makes it possible to manipulate the data by changing grayscale values. Interpretation is the critical process of making sense of the data. The first application was that of aerial photographic collection, which used the following process. Spatial measurement through the use of a light table in both conventional single or stereographic coverage, added skills such as the use of photogrammetry, the use of photomosaics, repeat coverage, making use of objects unregistered trademark known dimensions in order to detect modifications. Image analysis is the recently developed automated computer-aided application which is in increasing use. Object-based image analysis is a sub-discipline of geoscience devoted to partitioning remote sensing imagery into meaningful image objects, and assessing their characteristics through spatial, spectral and temporal scale. Old data from remote sensing is often valuable because it may provide the only long-term data for a large extent of geography. At the same time, the data is often complex to interpret, and bulky to store. Modern systems tend to store the data digitally, often with lossless compression. The difficulty with this approach is that the data is fragile, the format may be archaic, and the data may be easy to falsify. One of the best systems for archiving data series is as computer-generated machine-readable ultrafiche, usually in type font such as OCRB, or as digitized half-tone images. Ultrafiches survive well in standard libraries, with lifetimes of several centuries. They can be created, copied, filed and retrieved by automated systems. They are about as compact as archival magnetic media, and yet can be read by human beings with minimal, standardized equipment. Data processing levels. To facilitate the discussion of data processing in practice, several processing A-O levels were first defined in 1986 by NASA as part of its Earth observing system and steadily adopted since then, both internally at NASA and elsewhere. These definitions are: a Level 1 data record is the most fundamental data record that has significant scientific utility, and is the foundation upon which all subsequent data sets are produced. Level 2 is the first level that is directly usable for most scientific applications. Its value is much greater than the lower levels. Level 2 datasets tend to be less voluminous than Level 1 data because they have been reduced temporally, spatially, or spectrally. Level 3 datasets are generally smaller than lower-level datasets and thus can be dealt with without incurring a great deal of data handling overhead. These data tend to be generally more useful for many applications. The regular spatial and temporal organization of Level 3 datasets makes it feasible to readily combine data from different sources. While these processing levels are particularly suitable for typical satellite data processing pipelines, other data level vocabularies have been defined and may be appropriate for more heterogeneous workflows. History. The modern discipline of remote sensing arose with the development of flight. The balloonist G. Tournarche made photographs of Paris from his balloon in 1858. Messenger pigeons, kites, rockets and unmanned balloons were also used for early images. With the exception of balloons, these first, individual images were not particularly useful for map-making or for scientific purposes. Systematic aerial photography was developed for military surveillance and reconnaissance purposes beginning in World War I and reaching a climax during the Cold War with the use of modified combat aircraft such as the P-51, P-38, RB-66 and the F-4C, or specifically designed collection platforms such as the U-2/Tier-1, SR-71, A-5 and the OV-1 series both in overhead and standoff collection. A more recent development is that of increasingly smaller sensor pods such as those used by law enforcement and the military, in both manned and unmanned platforms. The advantage of this approach is that this requires minimal modification to a given airframe. Later imaging technologies would include infrared, conventional, Doppler and synthetic aperture radar. The development of artificial satellites in the latter half of the 20th century allowed remote sensing to progress to a global scale as of the end of the Cold War. Instrumentation aboard various Earth-observing and weather satellites such as Landsat, the Nimbus and more recent missions such as RADARSAT and UARS provided global measurements of various data for civil, research, and military purposes. Space probes to other planets have also provided the opportunity to conduct remote sensing studies in extraterrestrial environments. Synthetic aperture radar aboard the Magellan spacecraft provided detailed topographic maps of Venus, while instruments aboard SOHO allowed studies to be performed on the Sun and the solar wind, just to name a few examples. Recent developments include, beginning in the 1960s and 1970s with the development of image processing of satellite imagery. Several research groups in Silicon Valley including NASA Ames Research Center, GTE, and ESL Incorporated developed Fourier transform techniques leading to the first notable enhancement of imagery data. In 1999 the first commercial satellite collecting very high-resolution imagery was launched. Training and education, remote sensing has a growing relevance in the modern information society. It represents a key technology as part of the aerospace industry and bears increasing economic relevance. New sensors, for example Terra SARX and Rapid Eye, are developed constantly and the demand for skilled labor is increasing steadily. Furthermore, remote sensing exceedingly influences everyday life, ranging from weather forecasts to reports on climate change or natural disasters. As an example, 80% of the German students use the services of Google Earth. In 2006 alone the software was downloaded 100 million times. But studies has shown that only a fraction of them know more about the data they are working with. There exists a huge knowledge gap between the application and the understanding of satellite images. Remote sensing only plays a tangential role in schools, regardless of the political claims to strengthen the support for teaching on the subject. A lot of the computer software explicitly developed for school lessons has not yet been implemented due to its complexity. Thereby, the subject is either not at all integrated into the curriculum or does not pass the step of an interpretation of analog images. In fact, The subject of remote sensing requires a consolidation of physics and mathematics as well as competences in the fields of media and methods apart from the mere visual interpretation of satellite images. Many teachers have great interest in the subject of remote sensing, being motivated to integrate this topic into teaching, provided that the curriculum is considered. In many cases, this encouragement fails because of confusing information. In order to integrate remote sensing in a sustainable manner, organizations like the EGU or Digital Earth encourages the development of learning modules and learning portals promoting media and method qualifications as well as independent working. Remote sensing software. Remote sensing data is processed and analyzed with computer software, known as a remote sensing application. A large number of proprietary and open-source applications exist to process remote sensing data. Remote sensing software packages include Tacit View from 2D3, SOCAT GXP from BAE Systems, TNMIPS from Microimages, PCI Geomatica made by PCI Geomatics, the leading remote sensing software package in Canada, IDRISI from Clark Labs, Image Analyst from Intergraph, and Remote View made by Overwatch Textron Systems. DragonIPS is one of the oldest remote sensing packages still available, and is in some cases free. Open-source remote sensing software includes Optics, Orfeo Toolbox. Others mixing remote sensing and GIS capabilities are GrassGIS, ILWIS, QGIS, and TerraLook. According to an NOAA-sponsored research by Global Marketing Insights, Incorporated, the most used applications among Asian academic groups involved in remote sensing are as follows: ERDAS 36%. ESRI 30%. ITT Visual Information Solutions ENVI 17%. MapInfo 17%. Among Western academic respondents as follows: ESRI 39%, ERDAS Imagine 27%, MapInfo 9%, Autodesk 7%, ITT Visual Information Solutions ENVI 17%. See also. References. Further reading: Campbell, J.B. Introduction to Remote Sensing. The Guildford Press. ISBN A1-57230-640-8. Jensen, J.R. Remote Sensing of the Environment, An Earth Resource Perspective. Prentice Hall. ISBN A0-13-188950-8. Jensen, J.R. Digital Image Processing, A Remote Sensing Perspective. Prentice Hall, Lentile, Lee B. Holden, Zachary A. Smith, Alistair M.S. Falkowski, Michael J. Hudick, Andrew T. Morgan, Penelope. Lewis, Sarah A. Jessler, Paul E. Benson, Nate C. Remote Sensing Techniques to Assess Active Fire Characteristics and Post-Fire Effects. International Journal of Wildland Fire 3, 319 €345 doi, 10.1071/WFO5097 Lillesand, T.M. R.W. Kiefer. J.W. Chipman. Remote Sensing and Image Interpretation. Wiley. ISBN A0-471-15227-7. Richards, J.A. XGR. Remote Sensing Digital Image Analysis, An Introduction. Springer. ISBN A3-540-25128-6. U.S. Army FM Series. U.S. Army Military Intelligence Museum, Fort Huachuca, A.Z., Datgler, A.U. Rice, J.P. Like, K.R. Johnson, B.C. Butler, J.J. Xiong, X. Best Practice Guidelines for Pre-Launch Characterization and Calibration of Instruments for Passive Optical Remote Sensing. Journal of Research of the National Institute of Standards and Technology 116, 612 €646 doi, 10.6028/JRES. 116.009. Ben I.G., Escada Fowler, Fontanes D. and Hong Nguyen A.T. Remote Sensing, a tool to monitor and assess desertification. Les dossiers de copyright Matix du CSFD. Issue 2. 44 pp. Cuenza, C. Zhang, J., Teslov, A., and SDECH, 2013, Thermal Infrared Remote Sensing of Surface and Underground Coal Fires. In Cuenza, C. and SDH 2013, Thermal Infrared Remote Sensing a Sensors, Methods, Applications. Remote Sensing and Digital Image Processing Series, Volume 17, 572 pp. ISBN 978-94-007-6638-9, PPA 429 a €451, Cuenza, C. and SDH 2013, Thermal Infrared Remote Sensing a Sensors, Methods, Applications. Remote Sensing and Digital Image Processing Series, Volume 17, 572 pp. ISBN 978-94-007-6638-9, Lasapinara, R. and Massini N. 2012, Satellite Remote Sensing, a New Tool for Archaeology. Remote Sensing and Digital Image Processing Series, Volume 16, 364 pp. ISBN 978-90-481-8801-7. External links. Remote Sensing at DMOZ, Free Space Images, International Journal of Advanced Remote Sensing and GIS.